Some things float in liquids and gases in spite of the force of gravity. We measure that force when we measure an object's weight. For example, gravity pulls down on this cube of clay with a force of 170 grams. That's its weight. Let's submerge our cube in water. In air, it weighed 170 grams, but now it seems to weigh only 50. Has the force of gravity changed? No, the downward force of gravity on the cube is still the same. But another force, called buoyancy, is now pushing up on the cube with a force of 120 grams. Buoyancy counteracts 120 grams of the cube's weight, leaving a downward pull of only 50 grams. All objects placed in a fluid are acted on by both forces, gravity and buoyancy. It's the balance between these forces that determines whether an object will float or sink. For instance, take the case of this research submarine. When it's first lowered into the water, it floats. The downward force of gravity on the sub exactly equals the upward force of buoyancy. But as water is allowed to fill its ballast tanks, the sub gets heavier. And when the downward force of gravity is only slightly greater than the upward force of buoyancy, the submarine sinks to the seabed 2,000 meters below, where it carries on research activities. To bring the sub back up to the surface, scientists aboard the research ship signal for weights to drop off the sub. Now the buoyant force is greater than the gravitational force, and the sub rises to the surface again and floats. Throughout its journey, whether the sub sank or floated seemed to be controlled by its weight. But if weight makes a difference, why does this sub float when this much lighter lump of clay sinks? Is it the shape? Let's change it and see. When we weigh this new shape, it still weighs 170 grams in air. And in water, it still seems to weigh 50 grams. Pyramid or cube, the buoyant force is the same. In fact, we could give the clay any number of solid shapes and the buoyant force would not change. Then could size make a difference? We can test this with 3 cubic shapes of different sizes. Their materials are different, clay, aluminum, and copper, and each one weighs the same, 540 grams. Watch what happens when we submerge all 3 in water. In each case, a buoyant force lifts up against gravity, counteracting some of the weight. But the largest cube seems to have lost the most weight, and the smallest cube the least. So it seems that the amount of buoyant force can be affected by an object's size. Let's check this with cubes of the same size. In this case, since the cubes are made of different materials, clay, aluminum, and copper, they all have different weights. Last time, the different-sized cubes lost different amounts of weight. How will the weights of these cubes change underwater? This time, cubes of the same size seem to lose the same amount of weight. So, buoyant force depends on an object's size. But size doesn't explain why the same person floats higher in salt water than in fresh water, or why an egg that sinks in fresh water is able to float in salt water. The buoyant force is different. The size of the egg hasn't changed, but something about the water has. To see what that is, let's take a 550-gram aluminum cube and compare its weight in 4 different liquids. Submerged in water, it seems to weigh 320 grams. Let's keep track of this on a chart. The cube weighed 550 grams in air and seemed to weigh 320 grams in water. So 230 grams were counteracted by the buoyancy of the water. Now we weigh the cube in salt water. "280 grams. That's less than it seemed to weigh in fresh water. So it seemed to lose 270 grams in salt water. In alcohol, we get a different result. 370 grams. The cube seemed to lose only 180 grams in alcohol. And when we immerse our cube in carbon tetrachloride, the cube seems to weigh only 200 grams. 350 grams have been counteracted by the upward force of buoyancy. But let's rearrange this chart to show increasing weight loss from left to right. Now, what's interesting about this arrangement is this fact. If we weighed equal amounts, say a cubic centimeter of each of these liquids, the alcohol would weigh the least, then the water, then the salt water, and then the carbon tetrachloride would weigh the most. And notice, the cube also lost the most weight in carbon tet and the least in alcohol. It lost more in salt water than it did in water, and in equal amounts, salt water weighs more than water. So, what does this show us? That buoyancy is affected not only by the size of an object submerged in a liquid, but also by the weight of the liquid that it's submerged in. There's a connection between these two factors. To see what it is, we'll set a beaker on a scale so we can weigh some liquid as we collect it in the beaker. First, we adjust the scale to 0 to compensate for the weight of the beaker. As we lower our cube, it displaces or pushes aside some of the water. And that water weighs 230 grams. We mark the level of water in the beaker. And we mark its weight, 230 grams. At the same time, we note that our cube seems to weigh 320 grams instead of 550. It seems to have lost 230 grams, exactly equal to the weight of the water in the beaker. Next, we try the experiment with salt water. It should be clear now what determines how much liquid is being pushed out of the container. It's the size of the cube. A submerged object always pushes aside an amount of liquid equal to its own size. That's why the same amount of liquid is displaced again. In salt water, this cube seems to lose 270 grams to buoyancy. At the same time, the cube has displaced an amount of liquid that also weighs 270 grams. With alcohol, the numbers are different, but the pattern is the same. The cube seems to lose 180 grams in weight, although it displaces the same amount of liquid as before. And the alcohol that it displaces weighs 180 grams. In every case, the buoyant force on a submerged object is the same as the weight of the liquid that the object displaces. This is known as Archimedes' principle, named for the ancient Greek scientist who discovered it. The principle helps explain why objects float or sink. For example, with most of the shapes we've tried, the lump of clay sinks. But watch. We change the shape like this. And what happens? The clay floats, because some shapes increase the amount of water an object displaces, and that increases the buoyant force enough to match the downward pull of gravity. Add water, and soon the weight is greater than the buoyant force. Archimedes' principle doesn't apply only to solid objects in liquids. It also helps explain the behavior of two or more liquids when they're put together. Watch what happens when we add water to carbon tetrachloride. In equal amounts, remember, water is lighter than carbon tet. So, according to Archimedes' principle, it should float on top of the carbon tet. And it does. Now we add a third liquid, salad oil, which is even lighter than water in equal amounts. At first, the force of its fall carries droplets of the oil down through the water and carbon tet, but the buoyant force is lifting the oil to the top of the column where it will float above the two heavier liquids. A tomato falls through the oil. In water, the buoyant force is almost large enough to support it, but not quite. It does float on the carbon tet. Glass marbles are heavier for their size than salad oil, water, or carbon tet. A strawberry is heavier for its size than the oil, but lighter for its size than water. A bird's egg is heavier for its size than either oil or water, but not carbon tet. And a cork is lighter for its size than any of the liquids. An object sinks until buoyancy equals gravity, and the object displaces its own weight. Archimedes' principle doesn't apply only to liquids. It also applies to gases. For example, an amount of hot air weighs less than the same amount of cool air. When a balloon is filled with hot air, the whole balloon with the hot air inside it weighs less than the cold air that it displaces. So the force of buoyancy counteracts the force of gravity. In liquids and gases, things float because of the force of buoyancy.